Hi everyone, today I'm going to be talking about my Level 3 thesis, Improving Diffusion Models using Guide Models Trained with Timestep-based Label Smoothing. So, diffusion models have recently emerged as a powerful and expressive generative modeling technique, and they are currently the state-of-the-art in tasks across a wide range of domains, including image, video, and audio synthesis. Image generative diffusion models in particular are a focus of our study, and it's also illustrated in the slides right here. The way it works is that diffusion models iteratively invert the process of adding noise to data. So we start with a sample of pure random noise, which is easy to sample, and then we iteratively apply this denoising process until the sample resembles the true data. In our study, we propose a novel methodology for improving the generative modeling quality of a foundational diffusion model. We achieve this by proposing methodological enhancements to an existing, well-respected technique for achieving this called classifier guidance, which we actually show that we outperform in a proof-of-concept setting using small diffusion models. But to understand our enhancements and how they work, we first need to understand a little bit about diffusion models. So, diffusion models consist of a reconstruction function, let's call it R, which predicts the clean, noise-free version of an input data sample, which in our case are all images. As mentioned, with diffusion models, we start with a sample of pure random noise, and what we actually do is we run it through this reconstruction function. However, the initial prediction for the clean sample tends to be imprecise and unrefined, and that's because performing this in one step turns out to be quite intractable. Thus, what we then do is we actually add in back some degradation using this degradation function d, which is parameterized with an intensity t, the time step value. And to be clear, this is just adding Gaussian noise with variance proportional to t here. So once we add in back this noise, we then again run this reconstruction function to get a more refined prediction for the clean image. We then add in back some degradation again, but this time with slightly less degradation, slightly less intensity, and we then repeat this process, and in this way we iteratively refine this predicted clean image sample. Now, with classifier guidance, we train a classifier which takes as input any of these intermediary predicted images, let's say for example this one, and predicts its class labels. So for example, this classifier, let's say it assigns reasonably high probability to 6, some probability to 0, and so on. So what we can then do is see which class label the classifier thinks is most likely for this intermediary predicted clean image, which, for example, in this case is a 6 right here. We can then update the image such that the classifier is more likely to classify the image as that particular label and nothing else. And this is done by gradient descent. So we actually backprop through the classifier and update the image in this way. And this is possible, of course, because the classifier is actually a neural network, which means that it is differentiable. So for ease of notational burden and for simplicity, let's call this process of updating this image in this way using a classifier, let's call it G for guidance step. And so what we then do with classifier guidance is that we interleave this guidance step, G, into the usual diffusion inference process. And in this way, the generative modeling quality is improved. However, the illustrations I've been referring to are actually just for illustrative purposes, and classifier guidance doesn't actually perform this well. Certainly not in only 2 steps that I'm demonstrating here. So it can be improved, and central to my thesis is asking the question, how can classifier guidance be improved upon? In particular, what methodological shortcomings are there and how can they be addressed so as to improve generative modeling quality? And I state this more formally in the research question on the slides right there. So to investigate this, we implemented classifier guidance on a proof of concept diffusion model that was trained on the MNIST dataset. And on the left here is an actual intermediary image from this diffusion model, and in the middle we have the predicted labels of a actual classifier trained, using the standard methodology for classifier guidance, and we see that actually this classifier is very overconfident. It states with nearly 100% certainty that this is a 7, even though actually looking at the image, it is a bit ambiguous. It kind of looks like a 3, maybe an 8, maybe a 7, so it's not so clear-cut. And it is clear, therefore, that the classifiers trained in this standard way suffer from overconfidence. And we actually highlight this overconfidence as being a key shortcoming of classifier guidance, and we propose that by mitigating this overconfidence, we can improve generative modeling quality, which is what we go on to show later. So, to understand why these classifiers may be overconfident and how we can handle this and mitigate this, we first need to learn about how these classifiers are actually trained. So let's think about this, and bearing in mind that this classifier is expecting as input these intermediary predicted images, and it needs to assign a label to these. Okay, so what should our training targets be? Well, this is what we do in the standard methodology. So the usual way of training classifiers in this way is that we actually assume that we have access to a supervised dataset with images that the diffusion model was trained on. So we have ground truth labels and ground truth images. What we do is we pick a random intensity t, or timestep t, and we degrade this image, and then we reconstruct this image again using the degradation and reconstruction functions respectively. And in this way we get this predicted intermediary image kind of sample, and we set that as the training target for the input. And we set the ground truth label as the training target for the label. So this is the standard methodology. This is what we propose. So we propose to actually also blend the ground truth label with a uniform distribution with intensity proportional to this time step value t. So essentially we're addressing the overconfidence issue by explicitly training the classifier to be less confident, and specifically less confident in proportion to t. And this follows the idea that the more we degrade a ground truth image, the less refined the reconstruction is going to be, and thus we are actually teaching the classifier to be less certain in those cases. So with higher t, we're teaching the classifier to be less confident. So how well does it perform? Well, here are the results. As you can see, with no guidance, we have that on the left. So this is just the foundational diffusion model trained on the MNIST dataset. The performance, the outputs for this are on the left. These are uncherry-picked outputs. So using a classifier guide model which is trained in the standard way, we have that right here. As you can see, slightly better, potentially. And then we have our techniques on the end here. MTNet prob I just explained. TNet is just a very straightforward, simple case of what I've just presented, where we train a discriminator rather than a classifier. So a binary classifier, you could say. And then we have evaluated this on the CIFAR10 dataset as well, right there. Okay, so we actually evaluated a bunch of generative modeling quality metrics on all of these different approaches. So this includes FID, clip FID, kernel inception distance, inception score, and precision and recall. And the main takeaway is that, on the whole, our techniques, both of them, consistently outperform both standard classifier guided sampling as well as unguided sampling. And so that's great. And that now brings us on to the demonstration. So this image that was in the slides just now actually is not just an image, it's actually part of the demonstration. We can actually change this slider right here to see if this thing will update. I don't think it is. Okay, it's just slow. Which can see the actual process, this kind of iterative denoising process, starting from pure random noise with all of these techniques. So with the usual diffusion model, and then with the standard classifier guidance, and then MTNet prob, which I explained, and also TNet right there. And yeah, so you can actually take a look at this denoising process. Very cool. Another thing that I would like to quickly demonstrate is this overconfidence issue. So here we have, on the left here, we have intermediary images. So these are predicted clean images. So the first intermediary predicted clean image happens to be this. It's not very refined, it looks ambiguous. However, the classifier trained with the standard methodology for standard classifier guidance seems to be very confident, or overconfident, I would say that this is an 8. Whereas the classifier trained using our methodology that we propose is hedging across a lot more classes and is not as overconfident. And we can see how these classifier outputs change as this intermediary image is iteratively refined, and this is how it behaves. A key thing to note here is that if we take a look at the prediction trajectory, that's what I'm calling it, this is basically what outputs the model is predicting. With the standard classifier guide model, as you can see, it's very spiky. It's a very spiky output, and it is switching between what it thinks is the most likely quite often. And with the classifier trained using our technique, these outputs are more consistent and more smooth as well, not as spiky. So obviously this word I said, spiky, is not scientific. A more scientific way of formalizing what I just mentioned is to actually measure a quantity called the entropy of the output, and entropy is just a formal measure of the uncertainty of a probability distribution. So a very certain distribution, so a one-hot distribution will have low entropy, whereas uncertain outputs will have high entropy. As you can see, with the standard classifier guide model, the entropy is often very close to 0, so it's very often almost producing one outputs, which means it is assigning 100% probability to a certain outcome. Whereas with the classifier trained using our methodology, the entropy starts off high, but then progressively decreases, so it becomes more confident over time, which is kind of the behavior that we would expect. It's more like the behavior we would expect. And so we have essentially stabilized or improved the quality or improved the characteristics of the guide model, and we find that this actually improves generative modeling quality. Let's walk through some other code. Actually, I would like to quickly walk through the inference code, because this is probably worth showing off. The inference code is so in general, the way I've structured the code is quite intuitive and idiomatic, and in fact, inference is this simple. It is just for I in range non-time steps, so for every time step, we do the diffusion step, we compute the guide model step, and then we update the image using the computed gradient, so gradient descent using the guide model, and then we add in back some degradation, which is this line right here. So it's very idiomatic, makes a lot of sense, and the diffusion model itself is also, and the guide model as well, are coded in a polymorphic style, so you can easily swap these out very easily, which actually turned out to be very useful for rapidly testing lots of different ideas. So that's the inference code, and if you like, we can just quickly run this to see the inference process in real time. So yes, this is real time. This is using a GPU on NCC, the supercomputer. That's what it looks like. Just to quickly demonstrate this traineval.py file, this is kind of a very important file. This is actually training the guide models, and after each epoch of training, actually hold on, while I'm talking, I'm just going to run this so you can see what it looks like. Train eval. It will take quite a while. I think it will take around 20 minutes per epoch per guide model. So that's running there, and what it does is, for the guide model that you specify, it trains the guide model using the process I mentioned, and after each epoch it evaluates all of these different quality metrics, FID, KID, etc. And again, the code is very idiomatic. The training code, if I can just find it, it's should be right here. train epoch. Yeah. So right there, so it's literally just a guide model train epoch, and then we call this many times. And everything else here is just kind of boilerplate code for setting up, logging, etc. So that's that file, and what that file actually does is it outputs all of these folders right here, and with all of these files, with all of the metrics in, and of course the weights. If the weights don't exist, they will be created by training the model. So this process can be paused and interrupted and started again, which is very useful. And this other file, viz2. This Jupyter notebook, what it does is it parses all of these text files. As you can see, this is all the parsing code. Load it into pandas data frame, and then these are the graphs that I showed in the presentation, and these graphs are also in the report itself as well. So that's all there, and the table is generated as well, the latex table right there. So yeah, so this is the demos. Feel free to play around with these sliders. Okay, let's just cancel all this because yeah, you get the idea. It will take around about 20 minutes to run. But yeah, feel free to kind of play around with these demos right here, and I would also be happy to take any questions that you might have. Thank you so much for listening, and yeah, feel free to ask any questions.